Thanks, Andres, for the invitation, and it's a great pleasure to be here. So I'm going to be presenting the history of Gaussian splatting. So Gaussian splatting is clearly the greatest scientific and technological success of my career. And it's interesting because a lot of people kind of tell me, oh, it came out of nowhere. And the goal of this talk is to explain that it didn't come out of nowhere and basically explain the history of the development. So just a little bit of background. So I'm a senior researcher at INRIA, which is the French National Institute for Research in Computer Science, and my group works on computer graphics. So what exactly is computer graphics and what is it that we try to do? A high-level goal is to create realistic 3D environments and allow real-time navigation. So I'm sure you're all familiar with the basics of computer graphics. You start with a virtual scene, you create a virtual camera, and then you get an image output. And this is done traditionally in the computer graphics pipeline with an artist who will create geometry, which is a mesh, usually made out of triangles, and then the artist has to define material properties, so wood for the door, marble for the floor, and so on, lights and cameras, so cameras where we're going to look at from, and the light in this case is coming from the room. And then you need to run a very expensive physics-based light simulation, this is an illustration of path tracing, to get the final rendering, which is hopefully realistic. Can we turn down the lights a little bit? I think that will help. And one of the problems that we've been confronted with over the years is how can we create these scenes very easily? And this goes back to my problem definition of the high-level goal. So my main motivation over the years has been to make it easy to create content for graphics and have real-time and immediate rendering, avoiding this light simulation if possible. And what I'm going to be talking about here is the specific solution of capturing 3D from photos or video, which recently has been called novel view synthesis. So how does that work? Let's say that you have a real scene, you set up a set of cameras to take pictures, then hopefully computer vision can find the positions of the cameras and create an approximate geometry. And then we can put all of this together. So you can start from the real scene, you get the real cameras. In a perfect world, you'd have a perfect virtual scene, and then you can look at it from any point you want. And that would be very simple. Unfortunately, that's not the way the world works, because computer vision does not create a very good geometry, and it's very hard to extract materials. So this is the state of things when I started working on this 20 years ago, more than 20 years ago. And what people started developing is what we call image-based rendering. So the idea is that, yes, the geometry isn't great, but we have lots of information in the images, so we'll just project the pixels from the images using the geometry into the novel view where we want to look at from, and then we just need to blend the input images. So you may be wondering, how is this relevant for driving simulation? So obviously context creation for driving simulation has always been an issue, and this creates the potential for relatively low-cost creation of environments. So this is an example from Wave. They don't actually claim it's Gaussian splatting, but we'll talk about that later. And as you can see, this actually looks extremely realistic, and it can be used in a virtual environment. This is a virtual environment that could be used in a simulator. So I'm going to start with a bit of ancient history. All of this started with the work of Paul de Bebec at Berkeley. And at the time, you had to click on the images to calibrate the cameras and create the geometry, and then he projected textures onto it, creating what at the time was just unbelievably realistic imagery. A few years later, we were looking at a slightly more complex case of capturing trees, so you'll notice we had to use a sheet to get alpha matting. And then we'd create a volume, and we could just project the textures of the images onto the volume, creating quite high-quality final renderings. And the volumetric aspect you need to keep in mind for later. Again, around this time, so in 2001, we started working on point-based rendering as a way to be able to render very large environments. And what's important here is these were the days of the first NVIDIA GPUs. And this was a complete revelation because before the NVIDIA GPUs, you needed 30,000 or 60,000 euros to get graphics. And that allowed us to change the way we look at things. So we were able to put these things together in 2001. Again, here you had to click on the images to calibrate them. But once you calibrated the images, you could just do a pretty brute force optimization and do point-based rendering of a captured scene. So what's interesting is that the basic idea is there. like 24 years or 22 years ago. But there was a lot of work to do to get to the point of Gaussian splatting. So a bit of a fast forward, all of this problem of creating the assets manually, like clicking to get the calibration and the geometry, was very painful. And thankfully, computer vision researchers developed structure from motion and multi-view stereo, so automatic camera calibration was possible. You just gave the pictures and it found the poses. And there was some level of geometry reconstruction, which typically took the form of meshes, which are usually triangles. And what's important for triangles for us, and we'll see later, is the fact that we can get normals from the meshes. Quick illustration of what structure from motion looks like. Here we have the result of structure from motion and a multi-view stereo mesh, which is good globally, but you can see that there are things missing, for example, part of the car, and you can also see that there are places where there's too much geometry. These should be individual leaves, and they're not. And the other aspect of structure from motion is that it creates a set of 3D points that are used for triangulation. So this was a major breakthrough, right? Suddenly, we had the capacity. When I saw this, I said, this is it. I can actually get what I want. I can use this for graphics. And we have these 3D points, which are very useful, but the meshes were not very good. So we had to develop ways of improving the quality of the images given these bad meshes. And we developed a technique here where basically we would take the 4 closest images and use a technique called as rigid as possible warping to get the best possible looking shape. And this allowed us to move around pretty far away from the input cameras with quality which was okay. And the important thing here is that we needed to use the per view information. So the input views, the 4 closest input views, has a lot of rich visual information in the pixels that compensates for the incorrect general geometry, which is kind of an average. So we're now at the time where basically deep learning appeared. And I was lucky enough to have enlightened colleagues who pointed me to this, and they said, look, you should be paying attention. Deep learning actually is making a huge difference. And the blending part of the images in the end can just be seen as a filter. And by 2016, 2017, we knew that neural networks, especially CNNs, could do this very well. So we developed a technique to solve the blending problem. So here, basically, you have the set of images, and then these illustrate the weights that were learned by a neural network by training on a large number of scenes. And this allows us to basically do a very high quality blending. And when we compare before to after, this is the same input. We can see that all of the errors that you got from the incorrect geometry are corrected by the neural network, but also by some additional processing. So deep learning solved this very hard problem of blending, which before was a bunch of hacks. Basically, you had to tweak parameters. It never worked very well. And for me, it was an eye-opening moment, right? It basically demonstrated the power of this deep learning technology and that it was and the methodology around it, and it was important to keep that in mind. And I wasn't the only person to notice this. So around this time, around 2019, 2020, image-based rendering got replaced by what started to be called neural rendering. So what's the difference? In neural rendering, instead of using the geometry here, you use a neural network, and you train the neural network using the real input views, so that then you can just query the neural network at a new position and get a new image. So that's all very well, but to do this optimization, you need to be able to have a renderer that is differentiable. And the way that works is that you just compare the output of the renderer with the input image, and then because the renderer is differentiable, you can update the parameters that you need with the backpropagation. The problem is that most rendering algorithms are not differentiable. Meshes have hard edges, which create discontinuities, and this is really, really bad for optimization. So thankfully, colleagues at Berkeley and Google developed in 2019, 2020, what is now like a monumental contribution, neural radiance fields or NeRFs. And the key idea here was a volumetric representation of shape. So instead of having surfaces and meshes, they said, we can just represent shape as a density, which will be predicted by a neural network. And the way it works is that you cast rays, so basically you have a position along the ray xyz and a direction of the ray theta phi. That goes input into the network, and the network then, for each one of these points and directions, outputs a color and the density. So this was pretty amazing in terms of results, right? Basically, these are novel view synthesis, they're created views, and they look amazingly good, right? And this was all very well, but as a graphics person, my reaction to this was, this is good, but why would you want to do ray marching in a volume when in the end you're trying to represent something that's a surface? And I wasn't really sure that neural networks were required. And these were part of my motivation to go beyond. So the work that led to Gaussian splatting was funded by my first ERC grant, which I received in 2018, where the goal was basically to treat uncertainty, and in the end we used deep learning to solve several problems, and I'll be talking about the view synthesis problem. So the goal was to move from image-based rendering to a different optimized representation. So we needed differentiable rendering for optimization, and we wanted to get rid of multi-view stereo and meshes, because meshes have this, they're inaccurate and they're hard to optimize. And the second element, which is extremely important, is we wanted it to be fast rendering, so no ray marching. And since we knew a lot about GPUs and we know how to do rasterization, this seemed to be the right way to go. But it was a long process. So first we needed to find a replacement for volume ray marching. So my students at the time, Yorgos Kopanas and Thomas Lankuru, who's a postdoc, came up to me and said, how about using point rendering? And my reaction was, are you serious? We did that 10 years ago, it doesn't work. So thankfully, this was the one time where I made the right decision. I said, okay, let's give it a try. And that was probably the best decision I've made in my career. And basically, the idea is that instead of using volume ray marching, we can go back to the point-based rendering techniques that I mentioned earlier. And the idea is that we have a splat. So what is a splat? In the original formulation, you took geometry, you placed these oriented points, little oriented disks, on the surface, which are oriented based on the normal of the surface, and then you project them to the screen and you reconstruct them with a Gaussian kernel. So to do this, as I said, you need to have these normals that have to be obtained, and they're typically obtained from the mesh. Why are splats useful? They have several interesting properties. The first is when you get closer, they become bigger, so they can automatically fill holes. And when you turn on a slant, they become thin, and this allows us to represent edges. And most importantly, they can be processed independently, and that allows massive GPU parallelism. But they have to be differentiable. Thankfully, colleagues at ETH developed a fully differentiable splatting pipeline, again in the context of geometry, so we had to adapt it for optimization and improving the quality of the geometry. So in the original formulation, it was easy because people were sampling an existing geometry and they just could do a weighted average to do during the splatting. But in our case, we have all these other, we're going to be having a bunch of these splats all over the place. We don't know which ones are in the geometry or not. So we have to do a technique which takes these into account, and we used front to back alpha blending to do that, which is a traditional computer graphics approach. But that's not enough, because some of these points are wrong, and we need to make them disappear. So to make them disappear, we add an extra parameter which is going to be learned in the optimization process or trained in the optimization process, which is opacity, and when it goes to 0, the points go away. And it turns out that this is almost exactly the same as the NERF image formation model. So Yorgos worked on 2 projects before coming to Gaussian splatting. The first was basically this idea of improving a novel view synthesis using points, and we're still in the logic of having information per view. So for each pixel we create a point, we'll use the multi-view stereo to project it to 3D, and then we can project it to the novel view. We rasterize this to get a point cloud, and then we use a CNN to actually do the rendering of the final image, and this is a fully differentiable pipeline that allows us, for example, to change the position of the points and put them in the right place if the original multi-view stereo is not good. There were several elements to the method. I'm just going to insist on one. So for each point and each pixel, we have a set of optimizable properties, and you'll see that originally this is pretty blurry. The textures are not very high quality. And as the optimization progresses, this is a visualization, we can see that the texture becomes clearer and clearer, and we get a sharp high-quality image, and this is what the neural network learns. And compared to the state-of-the-art at the time, we have much better quality in the vegetation, and even compared to NERF, we had better results. So if we look at this first result of that PhD, we were able to correct some of the MBS errors. We have rasterization for differentiable rendering, and the convolutional neural network provides sharp, high-quality results, but we still need per-view information. So why is that a problem? It means that you need to load all of the input images to the GPU, so you're essentially limited to 300. You can't go beyond that. And then the CNN has flickering in motion, and that's a well-known fact. And the most important thing is optimization was still very slow. 18 hours per scene, it was equivalent to NERF. And even though we were much faster in rendering, 5 FPS is not what you can use in a simulator. So the next project I won't talk much about. It was about shiny objects. There were two elements of this project which were important. The first is we realized, so Yorgos one day said, I'm going to try optimizing without the per-view information. Just put all the points in 3D and optimize. It just turns out that it worked. So we no longer needed the per-view information. We got rid of that. And then we tested different neural architectures, and we found that multi-layer perceptrons were much better. And we got better results than the state-of-the-art at the time. So we were able to get rid of the per-view information, and we had the elements that I said before. But optimization was still slow, and we still needed the MVS meshes to initialize the circles with the normals. And this is one of the things which is an important lesson, is that because optimization was slow, it took 18 hours to do a cycle of experimentation. So we actually tried 3D Gaussians in this project. We tried it for a week. We had like 5 or 6 goes at doing it. It didn't work, and we let it go, right? And that is an important thing to keep in mind. So this brings us to the actual Gaussian splatting technique. The goals were to remove the meshes, multi-view stereo, move to 3D, to a primitive that is actually a 3D primitive, and remove all neural rendering components so that it will be fast, efficient, and accurate. And just as a little preview of the results, compared to the method that was presented the year before, ours was published in 2023, we can see that we were better quality overall, although the lights don't help, and we have about 10 times faster frame rate. So how did this work? Basically, extending 2D circles to 3D Gaussians is relatively straightforward. The formulation is very similar. Instead of using normal and standard deviation, you directly have a covariance matrix in 3D. And this allows you to model the space better. And instead of having a feature vector like the one that we optimized that I showed previously, we just use spherical harmonics because it's faster and it's a typical way to represent directional information in computer graphics. So we built on our computer graphics knowledge. So we don't need normals anymore because we have this 3D ellipsoid in space. And we start with isotropic versions, so little spheres. And we'll see that this approach is very good at representing thin structures. So this is an illustration of the SFM points that we start with, which come from the camera calibration. Then the optimization process turns these little spheres into these elongated ellipsoids, so it will fit the geometry of a scene very closely. And we will also need to add more points. I'll explain briefly how that works later. And then using the splatting approach, which is this volumetric rasterization, we get high-quality images. So how do we render? First, you need to do a sorting step. So what we do is an approximation. In the previous project, we were sorting per pixel. Here we sort globally, but it works well enough. Then we splat, and we do the alpha composite. So how did we go from 5 frames per second to 100 frames per second? It's kind of a big change. And that also means that from 18 hours of optimization, you can get optimization done in 5 minutes. The first thing was to use the GPU efficiently. The GPU is a massive multiprocessor. And it's tricky to keep all of the cores in the GPU busy at the same time. What we were doing before is we were sorting for every pixel, which basically means that all of the cores were waiting for the slowest core to finish. And it didn't distribute evenly over all the cores. So first you need to basically split the image into tiles so that the load is distributed well, and do the global sort, which can be done very efficiently using well-known algorithms on the GPU. So we optimize using all the properties, opacity, position, covariance, spherical harmonics, and this is where we use the standard deep learning machinery. So Gaussian splatting is not an AI technique. We don't have any neural networks, but we built on the deep learning methodology and the machinery, PyTorch, Adam, and so on. And we use a typical L1 loss plus a perceptual loss, which helped. So just one element of the algorithm, which is also interesting in addition to the GPU rendering, is the fact that if you do the naive solution just optimizing using the SFM points, it looks okay, but there's a lot of stuff missing. So we developed a way based on the gradients of the position to add points, which is called densification. And even though it's not the most intelligent algorithm, it works very well. So this is just a visualization of what the optimization looks like very quickly on one of these standard data sets. And we evaluated the method, and the reason I'm talking about evaluation is that there is one critical point which is very important, was that we decided, and we were very careful, to evaluate on 3 very different data sets. So each one of these data sets has very different properties. The MIP-NERF data set was basically designed for NERF, to make NERF look good. So that was my motivation. I said, well, we're not just going to use that. And we chose 2 other data sets which have different properties. They're outdoors, they're big, and the other one is indoors. And that allowed us to get parameters that worked very well everywhere. The results were great. So basically, compared to MIP-NERF 360, we have essentially almost the same PSNR and even better perceptual quality. And most importantly, to get that quality, MIP-NERF required 48 hours, and we're at 40 minutes. But we can see that instant NGP does optimize in 8 minutes, and it turns out that's the plateau. Even if you continue optimizing with instant NGP, it still doesn't get any better. So we said, okay, we can spend as much time as instant NGP to do the optimization, so 6 compared to 7 minutes, and let's see what happens. So we have slightly better quality in the metrics, but visual quality a lot better, and we're still much faster in terms of rendering. The only problem at the time was memory consumption, which has been solved since. So these are the slides that I'm really, really proud of, right? Here we are, 2 years earlier, Google, which is has enormous resources, has this solution, and 2 years later, there's this small lab in the south of France that's able to create a method that is basically in 40 minutes does the same thing, is over 1,000 times faster in rendering. And even compared to NVIDIA, again, not a small company, that published the year before, with the same amount of time, we have 10 times faster rendering and much better visual quality. So basically, this method found a very good sweet spot between volumetric rendering using opacity and the alpha blending technique and traditional rasterization, which was splats. It's one of the rare cases in my career where I have a method that is better both in quality and speed. That almost never happens, right? But it's good when it does. And the fact that we don't have neural networks is important because basically, instead of NERF, which is this big black box, you actually know where things are. It's interpretable and easy to use. Memory was still high, but as I said, that's been solved. It's being used in all the graphics engines. Our code was licensed free for research, pay for commercial. Several companies adopted it, so this one is a special effects company, so this is not a video, right? This is a 3D environment that you can navigate in freely, which is dynamic with multiple cameras. Vario has a teleport product that allows people to reconstruct environments and investigate. And Dolly has an e-commerce site, and these are just some examples among many others. Other companies have also used it, so Meta Hyperscape uses Gaussian splats, Adobe uses Gaussian splats for generative 3D. And as I said, Wave has this thing which they don't say if it's Gaussian splats, but when we stop here, this looks very much like Gaussian splats to me, so I'm pretty sure this is Gaussian splatting. And there were other cases, and it's a very interesting case for this in this context, where basically we can see the possibilities, even used in journalism. So there's a lot of scientific take-up. I'll just talk very briefly about some recent enhancements. So one is the ability to move around in large scenes. So here I took basically 40,000 images on a bike, and you can move around in something like a few kilometers of road interactively. And most recently, we came up with a solution to the remaining problem, which is the cost of calculating camera poses, which is still 5 minutes to several hours, and so is the optimization. So the goal was to have Gaussian splatting immediately after capture and available during capture, and we actually have a startup project on this technology. So here you see an illustration of the process as I'm advancing here in the room, taking the pictures, and you can see that as I go around, the environment, so on the left is the phone camera feed, and on the right are the Gaussian splats that are displayed to the user in real time. And after this capture, we have a pretty good, immediately after, we have the pretty good reconstruction. So just a few words about the future. I was lucky enough to get a second ERC Advanced grant, which started last year. And the goal is to look at how we can use the generative models and combine them with physically based solutions. So I won't go into details, just show one example of work that we've done already. So this is basically a capture with one lighting condition, but we use a diffusion model to generate different versions of different illuminations, which are guided by the position of the light illustrated here. It's not physically accurate, but it does give a very realistic effect. And this is just sort of a word of warning about video generative models. So here, I'm not sure if you've seen things like this, you basically define an image of a character and a location, and you can choose different locations that you want, and then you just basically prompt the system and say, generate a video. And this is the kind of quality that you can get for the different environments. Anyway. So those representations are very interesting, but the problem is that they're either good for rendering or good for optimization, but not both. So we need to design fast and accurate differentiable renderers, and that's very hard. And the hope is that with these differentiable renderers, we will be able to control generative models, and that's the goal of our project, although it obviously is very long term. So in conclusion, so novel view synthesis now is clearly, thanks to Gaussian splatting, usable in many applications, but it took more than 20 years. So is this actually solved? I don't think so completely. Camera calibration is still slow, even though our recent work gets rid of that. Relighting still needs to be controllable, and we need to be able to use this in physically based rendering. So in terms of just the keys to success, and I'll wrap up, I'm a little bit late, it's important to be mindful to the changing field. It's very difficult to have a good balance between adopting powerful new tools, which needs to be done, and we need to be very mindful in looking at what that's out there, and just jumping on the trendy wagon that everybody tends to do. And that's kind of what we managed to do. On the one hand, we were looking at NERF, but we developed something new. It's important to exploit your strengths, so we had core graphics, and that still has a lot to offer. And there's this balance between advancing quickly and leaving optimization till later. And as I showed in the talk, the fact that we could optimize fast allowed the algorithm to advance much more rapidly. So it's important to acknowledge your errors. I was wrong about points, but the fact that I realized that has now made me better at understanding these things. The ERC is a great solution. The EU has really done one thing right, and it was important to have small, flexible teams for me. That's my personal taste. And most important of all, you have to have fun. If you're not having fun when you're doing these things, you cannot do good research. Thank you very much.